everything that you're doing. And thank you so much for the awesome presentation, and keep making GiftBot awesome. I love it. Thank you so much.
Thank you so much.
All right. All right. Awesome. Well, I'm really excited because I get to go eat dinner. That is correct. I get to put food in my face, and that's really exciting. But I have one of my other best friends in the entire world, John Galloway, with me.
Hooray! It's a party.
And your computer's working now.
My computer's working. Yeah, I had right before the call, my computer blue screened and someone stopped at our house to pick something up and their car died and they were trying to jumpstart it. And I was like, kind of got this thing. But yeah, it's all working now.
It's all working. Hey, that's just what is today? Wednesday, Thursday? Who knows? All right, John. Well, I'm going to transition over to you. Thanks, everyone, for hanging out with me for the last 2 hours. And have a good one, John. See you.
Yeah, have a good dinner. Yeah, well, this is great. Thanks for joining the party. The .NET Conf is not done yet, and we're excited. I'm going to be bringing on Robin, and Robin, you are going to be blowing our minds with some cool stuff. So you're going to be teaching us about using Antlr to parse text.
Yeah,
is that right? So that sounds amazing. I've read about Antlr and been scared off every time I've looked at it, and I've also written text parsing code that I'm sure my code has scared other people. So I'm excited to see you teach us the right way to do this.
Okay, well, let's start. We're going to go, like you said, crashing through some code here.
Wonderful.
So let's start.
You can hit sorry, but before you get into it, hit that little hide thing down at the bottom.
Oh, got it.
And that'll free it up. Awesome.
Is that better? Okay. So I'm Robin. I'm a content PM at Microsoft. I work on Dynamics 365, and I work on developer content for the product. And recently I had a bunch of content in Markdown that I needed to move to XML. And also recently I'd taken a compiler class at Georgia Tech. And so I said, well, you know what? I think I can use Antlr for this. So let me give it a try. And let's go on to the next slide. So people mostly think of Antlr as a parsing tool for programming languages, but you can actually parse any kind of structured content, text or binary files. And you can find sample grammars for all different kinds of languages. And I even found one for Morse code. I didn't find one for Markdown. So I decided I would use it to solve my little problem. So first, let's look at a really basically simple case of using Antlr before we get into the full thing I had. So the basic workflow is you create a grammar. It's a little file that describes your language or your content. And you run it through Antlr. As they say, that's basically a command line program. You say, Antlr, here's my grammar. And it spits out a bunch of code in Java, C#, Python, whatever language. I decided to use C# this time. And you get a number of things. The one we're going to work with is the lexer, the parser, and the visitor. And so what are those and what do you do with those? So you take your input. In our first example, we're just going to take 4 plus 5. And you run it through the lexer and it creates tokens. And tokens you can think of as little chunks of content, words basically, words and punctuation. And then you send that to the parser, and the parser understands how those tokens fit together, how 3 different tokens create, say, a variable declaration or a function header. And it runs through all your input and it creates a tree for you. And so then what you do is you visit your tree. You basically look at each node in your parse tree, and then you spit out whatever it was you really wanted. So in this case, we're going to look at 4 plus 5, and what we really want is 9. So what does that look like? So on the left, you can see the grammar that handles this case, and on the right, you can see the parse tree that's created. So we're starting at kind of the bottom of the grammar. You kind of build up. On the one hand, your tree is created. You think of it top down, but you also kind of work from the bottom up. So first, we're going to ignore white space. I don't care if there's a tab or a space between 4 plus 5. And then what I know is I have integers, and then I have a plus sign in between. So those are the tokens I'm going to create. And then we also know those are lexer rules because they're capitalized. It's a convention in Antlr. And then we start making our parser rules, those things that we build the tree, that we actually build the tree out of. And so we really only have one parser rule in this case. And that's the equation. It's an integer, a plus sign, and an integer. And we call our entire grammar addition. It has to have a name, it has to have a start location, and in that case, it's equation. So what does this look like once we get into Visual Studio? Go to Visual Studio. Okay, so here I've got a little C# program, and here's my grammar again, and it's not so colorful because it's not in VS Code. And so you run Antlr on it, it creates a bunch of C# files, it also creates a bunch of Java files, and then you just compile those, and now you can run the test harness. I can show you how that works. Then you simply run a little command, and you tell it, I want my addition grammar and the equation rule, and here's some inputs, 4 plus 5, and then you just enter that. And you wait a second, and you get this in a nice little tree inspector, and you can click on things and see the whole thing. And that's really handy. I haven't had to write any C# code yet. I just wrote my grammar, and now immediately I can test it, and I can start working with it and get the tree to look like what I think works for what my problem is. So now I created a C# application so that I can now do something. Now I've parsed it, and now I want to get my number. So what I did is I created a C# console app using the .NET framework. I added a reference to Antlr using NuGet. That was pretty simple. And then I just added all those C# files straight off the disk. And so what I've got is like I said, a lexer. So these are generated, which means you don't want to change these, because every time you go back and change your grammar, they get regenerated. So you just want to leave those alone. Then there's the parser we talked about. There's also something called the listener, and we're not going to talk about that today. And then there's a visitor, which is an interface. And you say, oh, what do I do with that? Well, they also give you an implementation of that interface. But again, this is generated, and you don't want to touch it. So what you do is you create a class that inherits from the base visitor. And that's what I've done here. And this is where my work goes. So I called it calculator because it's going to add 2 numbers. And it derives from base visitor. And it's going to return an integer because we're going to take those strings, we're going to convert them to integers and return the sum. And we only have one rule, so that it creates one method. We're going to visit the equation as we're going to visit each node. And then it has a parameter called context, and the context knows about all the things in that rule, and that rule had a couple of integers and a plus sign. And so we just grab the 2 integers, basically. We turn them into, well, they're 2 strings that have digits in them. We turn them into integers, we add them up, and we return that value. So now how do we get the output? How do we get that number back? So here's sort of the basic plan when you're running Antlr. And if you think back to that workflow, it fits right in with that. I've got some input, got to turn it into a character stream. I need to create my lexer. I give it that stream. Then I want to create tokens out of it. And so I create a token stream and give it my lexer. Then I take those tokens and I can create my parser, because remember, we feed the tokens into the parser. And then I basically visit equation in the parser, and it builds the tree. So now I've got a tree. So then I send that tree over to my calculator. So I create, I just create one, instantiate it. I visit it, so it starts at the top, it starts at equation, visits equation. And then, we return that integer. So now our integer should be right there. And then we can just do a write line. So let's run that and see what happens. And there we've got it. 4 plus 5 equals 9. Exactly what we thought. Okay, so that was kind of interesting and fun and short. So what was our real issue? So the real issue was I had a lot of Markdown, and I needed to get it into XML. So let's take a look at what those files look like. So I'm going to go over here. So this is what our content used to look like. We had a file. It had the name of the class. It had the syntax for the object. There were some remarks. Sometimes there would be a little short summary right here. There were examples with code. There was a list of the methods. And then there was a heading for each method. We listed each method and its parameters and its return value. And we had a little tiny table of contents, but they weren't really connected to each other. So if I had a parameter that was, say, an integer, it didn't connect to the integer class so that you could go learn about integers. And they weren't arranged by namespace. So I wanted to pull it in together. And then this is what it looked like, quote, underneath. This is the actual authoring markdown that we used. There was a header at the top with some publishing things for search and who owned it and whose work it is. And then here's the content in Markdown. I don't know if you're familiar with Markdown, but it's basically a plain text way of creating content. So there's a lot of pound signs for headings. And then you use these bars to create tables. So the content was very structured because we had previously created it from a tool. And so I thought, well, this might work. There's one little thing we had to keep track of, though, is that code is specified in Markdown by being indented. And that's going to come back later in this process. So that's what we started with. And this is the new content we have. And because the new tool actually reflects over the DLLs, it gathers all that information about inheritance, and we make sure we have all the current properties and methods, and everything links to each other. I have the overloads. I can click off into the .NET framework because our APIs are all managed. So we get a lot of that. And, we again have our small table of contents here. We can see up here which namespace we're in. And then every time our DLLs change, we could rerun this and it updates all the properties and methods and stuff. So we really wanted to move over here. So then we looked at, well, what does that authoring look like? So let's get a little bigger here. And so that's all in XML. And then the documentation is in some of these tags, but this doesn't format as well as we can find it over here. So let's go look in Visual Studio Code, and this is the same file. And so you can see there's lots of stuff. There's the name of the class and all the different type signatures for the different managed languages. And then we have a docs element here. This is at the class level, so each one can have a summary. This one was empty. It can have remarks, and that's where we put not only the remarks, but also the example sections. And then I notice another thing we did was, instead of just using indenting to mark code, we actually used what they call fencing, which are the 3 back ticks. And then we put XPP here, and that gets us code highlighting that's specific to X++. So that's what we wanted to do. So we looked at the markdown, the format. So I just parsed it with Antlr. So let's take a look again over in VS Code. VS Code here again. VS Code has a nice extension for syntax highlighting of Antlr. There's also an extension for Visual Studio, but I haven't installed that yet, just because I haven't. So here's the grammar. What I like about the Antlr grammar is it kind of looks like your content that you're trying to parse. So here's the input file. We did a little pre-processing because it was worth doing a little pre-processing. We took out that header at the top. There's no need to, since it was so easy to remove, we just removed it. We didn't need any of that information. It turned out to be a little tricky, actually, to deal with those multiple pound signs. There was 1 pound, the heading 1, 2 pounds for the table and each method, and then 3 pounds. So it was actually pretty easy to go through and put words in there that were really easy to find and were really easy to parse on. And it turns out there wasn't really a huge amount of different things in the file. We basically got, we had the class name and a little summary about it, maybe some remarks and an example, and then several methods, and each of them had maybe a summary and remarks and an example and parameter names and descriptions. And that was basically it. So you can see we've only got about 14 or 15 different rules here for those things. And almost every one of them has something called content. And that's basically the documentation, the markdown that we wanted to pull out. And so content is ID, which you can think of as word, plus a whole bunch of different punctuation, and then some special words we needed to capture because they were often used in the signature, the method signatures. So those are the rules. And then there's some Lexer, things going on down here, some tokens, just to deal with the punctuation and the names. So that's what the grammar looks like. It's fairly simple when you get down to it. Let's go. So here we go. And so back to the demo, right? So now we'll go back to Visual Studio again. So there's the grammar. Again, we've got our Lexer, our parser, our parser. The listener we're not going to use. We've got the visitor interface and the base visitor. And then I created the listener, the custom listener. So the plan was I would parse up the markdown, and then I created a class called system class, and it basically held all the information I took out of the markdown. So using the parser, I could find all the different pieces of documentation I need, and then I put it in this class after it's all been, I fixed all the code and everything. And then after I've gathered it all up, I've got to write content. I send it an XML document, and using XPath, standard kind of XML XML handling in the .NET framework, I could just inject all those bits of markdown into the XML, which was really pretty easy. There's not even a lot of code there. So that's the system class, and the system includes a bunch of methods. The class, includes a bunch of methods. So that means most of my work was in what I called the topic visitor, which again inherits from the base visitor, and then you just override the pieces you need. Where was I? So when I open it, I send the system class so it can fill that in, and then I need to send the actual original content stream, and I'll talk about that in just a minute. And then I visit the top node. And so this is, once you start visiting the nodes, this is where you have to decide how you're going to visit all your nodes. There's a method called visit children. You could visit this node and then do the work and then say, go visit all my children. And then the children do whatever they need to do. So in this example, the class is at the top, and then it's got methods, and you can visit those. I should show you one of those. And so the work goes on here. So you have to decide, are you just going to go straight down the tree, or do you want to have more control in the sense that I'm not just going to let it go visit whatever it wants recursively. I'm going to see if there's a summary. I'm going to see if there's examples. I'm going to see if there's methods. And so I've written code to do those specific things. So if there's an example, I'm going to go visit it. If there's remarks, I'm going to go visit it. And if there are any methods, I'll go visit those one by one. So what was I going to say? Oh yeah, so while I'm here, let me show you. So remember we were looking at, I think it was field binding, and we had the grammar. It's all been compiled. We can run this little test tool, and we can see the entire class here is a tree, the entire file. And so, like I said, it wasn't very complicated, so it isn't very deep, but it's very wide because there are a lot of methods. But fortunately, we can go over here and we can navigate through and just see one method at a time. So here's the pack method, and we can see it's pack content, and here's a little string of some documentation, and then it's got the method signature, it's got a return value, and here's a little bit about the return value. So we can check our grammar to make sure it's okay that way. So anyway, there was one other thing I wanted to mention about going through this that was kind of interesting, because basically, you look for the remarks and examples, and you look at each method and it has remarks and examples. So remember I talked about the actual markdown itself. And it turns out that markdown formatting matters. So it matters where the carriage returns are. It matters when you have tabs and spaces. And it matters about vertical bars. And so you can't just, remember we stripped out all the white space, which means all we get in the parse tree are all those individual tokens. And when you have code, it's just basically an array of parentheses and curly braces and semicolons and words. And so I need to go back and get that markdown back, the actual markdown. And so it happens when I want to visit, say, especially examples, because the example section has that indented code, is I go and I visit the content. Go to definition. And from there, I using the original string, because we passed that in when they build it, you can look at the beginning and the end of that node and get all the content that was there originally. And it turns out, in my class, we also, we parsed the whole language, and it was surprising how many times we kind of had to go back and get the original content, even though we parsed it. So maybe we weren't, quite there yet, but it comes up. If you start using it, you'll end up on Stack Overflow wondering how to do that. So then once I had the original content, then I could parse the example. I wrote a little method to do that. Go to the definition. And so once I had the original, I could go through, and where I found indentation, that meant it was a code example, and I could add the fencing around it and do that. Another way to handle it, I could have written a second grammar, and then I could have passed my original string to a second grammar, and maybe that second grammar wouldn't ignore the white space. And in that case, I might be able to get that information without having to, again, here back we are parsing, strings again, and do that. So we've run through everything. Let's take a look. So now we can run it. So we go over here to, where are we? Looking for program. It's console app. I call it program. It's a lot of housekeeping and a little bit of Antlr. So down here in the middle, again, we saw that in the example. You create the lexer and the parser, and you send the tokens. And the rest of the code basically just opens up all the files and finds the XML file that goes with each markdown and fills it in and saves it out. And then, sometimes things don't match up, and it creates a list of problems, and also a list of who's going to have to review them, because we had 475. So we can run it, and it's going to go through 30 or so, at least it did earlier today. Not all that necessarily exciting to watch it run. We can go see that the file updated right now. We can open it up in let's open it up in Visual Studio Code, because it has nice highlighting there. And you can see here's my new code added in here in Docs. And that's basically it. That's the way it goes, kind of the crash course. And so the work was done fairly quickly. It was a lot of fun, I thought, rather than like having to grind through a lot of string manipulation code, which I actually like. But I thought this was a lot of fun. So here's some resources. There's a lot of sample grammars out there on the internet. There's the C# target, they call it. The Antlr book is great. Highly recommend it. And it's on O'Reilly Books if you have a subscription to that. So questions?
Wow. Yeah, that was fascinating. Let me see. So we had just one come in. A reminder to people watching, ask your question using .NET Conf. And not only will you get it answered by these brilliant speakers, but you will also get entered for fabulous prizes in a drawing. So this was a question about converting from XML to JSON.
Okay.
And yeah, I don't know. I could see that you could do that. I guess there's other ways also that you can convert from XML to JSON. What would your thoughts be on that?
So first of all, I know if you go to the sample the sample grammars, you can find a grammar for XML and you can find one for JSON. That's probably not the way I do it, because you can read XML. There are XML readers in the .NET framework, and there are JSON readers. So you could create an object that goes in between and save them out. You could certainly do it. And it's interesting because I had talked about whether you should walk through your nodes purposefully, or whether you should kind of let it go recursively on its own.
Mm-hmm.
And XML is a format where I think letting it go recursively on its own kind of works, because everything has to be properly nested. So that would be interesting, yeah.
I personally thought that was fascinating. Normally they talk about how crazy it is to try and parse HTML because it can be all kinds of crazy stuff, but Markdown is kind of scoped down in a way that you were able to make it work. Did you run into problems with escaping or any kind of, like weird edge cases?
Oh yeah. Okay. Do you want to actually see that code?
Sure. Why not?
Okay. So let me see if I can find it. Yeah. So there's some issues because obviously Markdown handles like greater than and less than differently than XML. And we don't escape it. No, sometimes we do escape it in Markdown. So somewhere in here, let's see if I can find it. I actually was able to call some functions from the .NET framework to handle it, but just, I'm in the wrong file. That would help. It's down here a ways. I'll try and find it. Remove empty. But yeah, I had to deal with that.
Yeah.
Sorry, I try and find it.
Well, and like a lot of parsing logic I've had to write, sometimes you're like, do I do it the absolutely perfect way, or do I just find this one little character that always fails and replace it with the right thing?
Right. And I'm looking for it and I don't find it, but I remember working on it, and I actually removed some comments related to it right before we started. Because remember, I also ended up putting it in C data tags. And once you put it in C data tags,
anything goes there, right?
Yeah, you don't have to deal with it. But I did go back and forth a few times trying to get that to work. Yes.
Okay. Had one other question come in. What's the wildest application of Antlr you've ever seen to parse what kind of text? I mean, maybe you've got the wildest application of Antlr right there.
I don't think this is the wildest. Oh, no, I don't know if I have an answer. I know you can parse binary inputs as well.
Okay.
I suspect there's, somebody parsed images, if I had to guess.
Wow.
And that could be interesting to look at how you would do that and what your tokens would look at, what your Lexer would look like to do that.
Wow. Well, that was
powerful. We've only touched, on what it can do.
Yeah, I think this is great. It's a really practical application, and it's also a great way to kind of expand my thinking. And viewers thinking of Antlr as not just a cog in the writing a programming language, like a traditional programming language, but it's useful for exactly the kind of thing you did.
Right. And it was a lot of fun because a lot of people, I think it's mostly Java. It's basically a Java task, but there's so many targets. There's even Python. I was using Python at the hackathon last summer. It's very flexible and powerful.
Awesome. Great. Well, thanks a lot. So we'll say goodbye to you and thank you very much. So our next up is we're going to be bringing on Andrew, and Andrew Nasenko is going to be speaking to us about combining asynchrony and coroutines. And I already said it's coroutines, right?
Coroutines.
Coroutines, great.
Yeah.
So, and this is a C#8 feature, correct?
That's a C#8 feature. Yeah.
Okay, great.
We'll cover that.
All right. So I will just bring you on and I will disappear.
Thank you very much. Hi, friends. My name is Andrew Nasenko. I'm a software developer and entrepreneur. My previous role was with Nuance Communications, and I used to work there for many years as a part of tremendous team of talented and wonderful people. I live and work in Australia, Australian of Ukrainian origins, and I'd like to say big thank you for Sydney AltNet, who were the audience for the initial version of this talk. And of course, thank you to my wife and to my son for their patience and for letting me prepare for this event. We'll be talking about asynchronous coroutines with C#. This is the first time I'm giving a talk on a global scale, and I'm a bit nervous, so I apologize if anything goes wrong. So any questions, you can easily find me on TechWeb by my Twitter handle. I'd be happy to follow up. So let's begin. I'd like to start with a very simple C# method for rendering fade effect in Unity game engine. So what's going on here? This sounds familiar. This is a numerator. This sounds also familiar. We all use link in C# to produce data sequentially. But why do we have this null as a result here? And the answer is Unity doesn't use this method for generating data. It uses it to suspend the execution flow of this for loop to be resumed later. So we actually see the fade effect on the screen of the game or whatever it is. What are coroutines? Coroutines are functions that can be suspended, resumed, and executed cooperatively, and often on the same thread. At least that's what Wikipedia says. And this is how they are different from thread routines, which are typically preemptively multitasked. Coroutines is nothing new. They are old and mature concept. I'm myself old enough to remember Windows 3 with its yield method. We used to call it when we needed to organize cooperating multitasking between all those apps. They were executed on a single thread. Luckily, nowadays, coroutines are easy to implement thanks to the modern language support that C# has, which takes excellent care of generating implicit state machine logic for our coroutine methods. What is a state machine? Let's have a quick look. And I'm using this pretty awesome sharplab.io website. On the left-hand side, we have a very basic coroutine, IAsyncEnumerable based. It's all it does, it just iterates with 80 steps and generates a string of a character on the console. At the right-hand side, we see what the compiler generated for us, and it's just a bunch of weird code. What it is actually, it's just like a hidden class with a bunch of delegates, callbacks. All it does is to allow us to suspend and resume the execution flow of this for loop. All right, so back to slides. What are coroutines useful for? Coroutines are useful, can be useful for script-like scenarios where we want to suspend and resume the execution flow of something after each logical step. And the nice thing is we have explicit control over when to resume the execution and when to suspend it. Many long-running background workflows can potentially be structured as coroutines. For example, spell checking pattern, syntax highlighting, static code analysis. One real-life example that I'm going to be cover in this talk is automated UI testing. Hopefully I'll have time for that. Let's do some coding. Let's start with a simple case, coroutines without internal asynchrony. This approach has been in use since yield keyword was introduced in C#, I believe it's version 2, so over a decade by now, and that allows to implement state machines for IAsyncEnumerable and IEnumerator methods. Traditionally, we used yield return for synchronous generation of data sequences. With coroutines, we use it as a tool to break the code into multiple individually executed steps. And as I said before, this technique has been popularized by frameworks like Unity Game Engine. There's also Caliburn Micro for WPF and some others. let's keep it simple. So this, back again to that coroutine A. Again, all it does is generates a run of A characters. In real life, it could be doing something like updating view model, for example, or anything else. But we want to keep things simple here. And just to show what it's about, we have also coroutine B that looks pretty much the same. It outputs a string of B characters, and we want them to run concurrently on the same thread. Let's go to Visual Studio and actually run the code. So I have this little Windows Forms application as a playground, and that'd be the first demo. So you saw the code, now they run in parallel. How do they run? There must be something that executes them, that drives them. Let's go back to the slides. The workflow goes like that. So we have that UI thread here. We have coroutine A that yields to B, B yields to A yields to B, and on and on. And the execution is driven by the code which we called coroutine driver. The purpose of it is to first of all start, suspend, resume, and end coroutines. In our example, it also combines multiple IAnumerables into a single sequence, because we want to interleave A at B. And then it executes that resulting sequence one step at a time by calling IAenumerable move next upon a certain time interval. The coroutine driver code looks like this. Actually, let's go to Visual Studio and have a closer look. So this is here. Yeah, as I said, this is the driver itself is a task-based method because we do something on particular timeline. We create that combined sequence of A and B here, get IAnumerable for it. We start the Windows Forms timer, and upon every single tick, what we do, we call move next on that combined sequence of A and B. And we do that in the loop. We do that until move next returns false, or until the cancellation token is signaled. So in our case, we just loop until I click cancel button. So that's nice and simple. Back to the slides. Why not simply use async await? So instead of using IAnumerable, we could have just created something like that, a simple task-based method that does something like await task yield inside. Why is it not so good? Because we only would be notified about the completion of the whole method, not about individual steps. We can potentially control individual steps, but for that we would have to enroll something like a custom task scheduler or custom synchronization context, or do custom awaitable instead of this task yield. All right. What if we still want to use asynchrony inside methods like coroutine A or coroutine B? It can be useful for many reasons. We want to wait for something like, I don't know, a WebSocket message or mouse move or keyboard button, and then suspend and resume. Ideally, we'd like to use async await for awaiting the result of actual asynchronous API, and use yield return for suspending the execution flow. Well, that wasn't possible until recently, until C# 8.0, which introduced language support for asynchronous iterators. And these are the things, a bunch of new interfaces and language features. They are nothing more than counterparts for for the things that we already know. That's IAenumerable, IEnumerator, IDisposable, for each, and using, but they are asynchronous. They don't block the thread, and they allow us to work with asynchronous APIs. Let's reproduce what we've done so far with IEnumerable based coroutines, but using IAsyncEnumerable this time. So we still want to have certain minimum time interval between yield return continuations, but to add some real asynchrony, we want to proceed to the next step when the UI thread is idle. Just something useful. We don't want to, we have background workflow, we don't want to spam the UI thread with work. And we also want to do that if there is no pending input on the UI thread message queue. So for that, I created a little helper class, which is called input idler. You can find it in my GitHub repo for this talk. And I'm going to use it inside coroutine A and coroutine B. So coroutine A now is IAsyncEnumerable based. There we have our little asynchrony here. We await the result of this input idler. And just as before, we just return the current for index as a progress notification. At coroutine B, we may want to change a bit to make it different. We want to slow it down because now we can. So we also add that task delay. Supposedly it will run slower than coroutine A. Let's do some demo. Same application, now the second demo. There we go. So they both run concurrently, still on the same UI thread. B is a bit slower. Now let's do that dirty trick to start working on the UI thread. This is not something that we all should be doing, but just because we can for this demo, that's what it does. It just does dirty work on the UI thread, and you can see both of them are on hold while the UI thread is busy. All right, so that's nice. Back to the slides. Yeah, it's actually also interesting to have a look at that coroutine driver. I believe it's got even simpler than for non-asynchronous version. So we have that drive coroutine async method that accepts a bunch of coroutines as IAsyncEnumerable, and then we start them all concurrently, and then we iterate through each of them using a wait for each loop. And that's our delay here, which is like now it's a minimum delay because we have no control over what's going inside coroutine. It may stop forever, so we at least provision for some minimum time interval. Now let's divert a bit and demystify what is a wait for each loop. Back to Visual Studio. It's very basic. It's very simple when you get down to it. So all it does, the for each loop accepts an IAsyncEnumerable cancellation token, and we obtain IAsyncEnumerator on that IAsyncEnumerable. So basically, IAsyncEnumerable is a factory for IAsyncEnumerator. And then we plainly loop through the next move next async. Synchronously, we await the result of move next async. If it's false, we stop. Otherwise, we just do something with that data that we received. So and also we can that can be synchronous, something that we do with it, or it can be asynchronous like that. Hope it makes sense. Back to the slides. Now the fun part. What if you want to synchronize coroutine A and coroutine B? Like A depends on something that is going inside B. We may say that coroutine A and B serve as producers to the coroutine driver, which is the consumer part of it. But both A and B run independently. They are not even aware of each other's existence. What if you want to make them aware of each other? We can't just pass IAsyncEnumerable for B into IAsyncEnumerable for A into B and vice versa. We can't do that. So we need some kind of buffer. And I come up with a special helper class for that, which is called IAsyncCoroutineProxy. It wraps a very awesome .NET channel class, which we'll talk about a bit later, as a synchronous buffer for buffering progress notifications of each coroutine. Let's have a look at the code again. It's going to be this demo. So what we want to do, still two console-based coroutines, but we want coroutine A to be on hold while B is progressing here. Then B is on hold, A is progressing, and then they both continue together. They kind of know about each other now, and they synchronize their workflow upon each other. And again, we can just do our dirty work on the UI thread, and they both on hold. And then when the work's done, they both continue. Let's look at the code. Oops, that happens. Yeah, before we look at the code, I want to touch a bit that channel class that I mentioned previously. So channel is like a pipe. We can push objects into one side of the pipe with channel writer, and then we fetch them as a synchronous stream from the other side of the pipe with channel reader. And so it looks like that. We have coroutine A, we have proxy for A, and we have coroutine B, and we have proxy for B. And the progress of A goes into proxy A, the progress of B goes into proxy B, and every time A wants to synchronize upon B, it speaks to that proxy of B. And the same thing is when B wants to synchronize upon A, it speaks to the proxy of A, not directly. Because if we did it directly, we could have end up as some sort of naughty asynchronous deadlock, which is fun to experiment if you have time with. Let's look at the code. So that'd be this one. And let's look at the code of coroutine A. So that's it.
Andrew, can you zoom in the code a little bit? I had a few people saying they're having trouble reading it.
Sure.
That's a lot better. Thank you.
Is that better? Sorry about that. So, all right. So that's coroutine A. It accepts that proxy, and the proxy is itself. We make it IAsyncEnumerable. Then for the first part, when the coroutine A is on hold, it just draws that little throwbar, like spinning wheel. It iterates asynchronously through B, and when the B is at step 4, it breaks out of this loop and it starts its own workflow. So it starts its own 80 steps, and we have a delay here, and it basically produces as a result the current iteration. Let's look at B. It's a bit different, but also pretty basic. So we have that for loop for 80 steps, and first of all, we just do our first 40 steps. When we are at step 40, we pause. We now start looking for coroutine A. And when coroutine A is step 40, we also break out of this and we continue our outer loop until we finish. And what's nice about this is instead of using a wait for each, we can actually use a synchronous link, and it's very powerful. I consume that system link async package, and now hopefully it will work. What I'm going to do is I'm going to do proxy A, take 40, take 40, excuse me, take 40, then I'm going to use last or default. I think that should do. And of course I need to await this. So there's not going to be this robber now, but let's have a quick run. Yeah, there we go, it stopped. No throwbar, but it stopped, and now it continues. So yeah, we can use a synchronous link, and it's very powerful. I only created the service myself, but I think it's pretty cool. So how much time we still have? Okay, back to the slides. Oh yeah, let's touch the base on what is that proxy code that uses the channel. The proxy code is actually pretty simple itself as well. All it does is it creates an unbound channel. An unbound channel is only limited by the amount of memory you have. You can push as much as you have memory available. And it exposes the reader end of that channel as another IAsyncEnumerable. So that's what coroutine B takes in when it needs to speak to coroutine A. And then basically it just uses another await for each loop to iterate through coroutine which it is proxying to. And writes the progress notifications to the writer end of the channel, and that it completes the channel when that sequence is complete or is cancelled through the token. So yeah, it's pretty simple as well. Now about real-world example. So I actually learned all that stuff when I started learning asynchronous streams in C#, and I wanted to apply it to something. And I have that side project that is a sort of copy-paste productivity improvement tool. I hate when I paste formatted text. I think everyone does. So we have Control-Shift-C that usually works, but sometimes it doesn't. Or sometimes you want to paste something into terminal window and it just get executed. So I wanted a little app to help me with my bad habits. And all it does, it just uses Windows Send Input API to simulate user input. It strips out the formatting from the clipboard and just spits it out character by character to the currently active app. And I needed I need a test for that, to automate the test. So that's what I come up with. So I have a foreground thread that has a Windows form containing just a text box. And then I have a background thread that calls send input. Maybe a decade ago I need to synchronize upon these two workflows, because I need to know when the window is ready to accept the characters, when the characters has been processed and sent back what actually is inside the text box. So I had to synchronize, and previously I would use something like manual reset event and wait one to block. And the thing is, these two workflows that actually run on UI threads, both of them. The thread that has a message loop, and by blocking it, I would have opened a box of worms. So, but luckily today I can use asynchronous coroutines for that. So anytime background coroutine wants to speak to foreground coroutine, I can send the message with this yield return, and anytime it expects something from the foreground coroutine, it does it through await get next. So let's have a look at the code. Let's go to the test explorer. Let's first have a run of it. So that's a foreground window, and the background thread just sends some input and multi-line input, and at the end of it. So it's very basic, but behind the scene there's lots of stuff going on. So I have that foreground coroutine, which is IAsyncEnumerable, and it has like 4 states. Ready state, text received, cleared the text, and the finish. And when it starts, it basically begins with it does yield return to return the message to the background coroutine that it is ready. And after that, it is suspended because we made the return. The state machine is in suspended state. We'll get to the background later, but the next step, when it is resumed, it now awaits for a message from the background thread to background coroutine to make sure that now the background coroutine is ready. So it awaits for a message, verifies it is ready, and that proceeds to the next step. And the next step, it again awaits for the message to get something that the text was sent. And when the text was sent, it actually reads the text from the text box and submits it back as another message as text received. And so it's pretty much linear workflow. We don't have even any loops here. Let's look at the background coroutine. So background coroutine is very similar. Also runs on its own UI thread. It has ready state, text send, finish state, and it also starts like notifying the foreground that we are ready, and then it expects a message from the foreground that the foreground is ready here, and then it basically simulates the typing by sending that text, and then it notifies that the text has been sent, and then it awaits for another message to confirm that the text has been received. It verifies we received what we sent, and stuff like that. So what I like about that, it's they actually run in parallel, not even concurrently, because they run on different threads, but they synchronize at particular points when they need to, and everything is non-blocking, so there is not a single bit of the blocking code here. I think I just scratched the surface of it. There must be, yeah, that's, if you like to make a picture, it will take you to my GitHub repo for this project. Summing it up, I think that asynchronous coroutines may help with structuring any asynchronous workflows, and including certain consumer-producer scenarios. They are especially handy where there is no clear role separation between producer and consumer. And similar problems, of course, can be solved by more like mature and powerful toolkits like reactive extensions or TPL data flow. But those might have a bit of steep learning curve. And here we just deal with language constructs, the syntax sugar that C# isolates us from. All the mechanics that goes behind the scene. And also this concept can be used with some other languages, those which support asynchronous iterators, including modern JavaScript. And that's it. Yeah, I have reference section. You can find all of that in my GitHub repo, and just if you need to get to it, just search for my Twitter handle. It's knows the ratio. Thanks for watching that. Happy to answer any questions.
Yeah, wow, that was really interesting. We got a lot of people saying they're drooling over it. It looks amazing. We had some other people saying, wow, this is a little confusing and it's a lot to learn. So I think I think we gave you a very short time to speak in, right? So you have to kind of pack
I
it
tried
in.
to squeeze in a bit. I could go on for more. But
well,
yeah, I mean, it might sound complex, but it's actually simple as you get to it, as with pretty much everything else, right?
Yeah, and I think it's great that you're providing that sample code that people can look at and test. I had a few questions. One is, are there cases where the overhead of adding in the async and the coroutines and that sort of thing, like, is there much of an overhead in doing that?
As my answer would be simple. As with anyone else, don't do micro optimization until you really need to do profiling. And there are lots of questions on Stack Overflow about that, and some of them I myself answered. It's actually, the overhead is pretty low if you get down to it. It's the convenience. I would pick convenience anytime over the overhead. Okay,
that makes sense. How do you showed some different options, like including link and like several things that you step through. How do you? I mean, the link example looks pretty simple. Just from a lines of code point of view, how do you choose between those different options?
To be honest, I only used asynchronous link in this particular example.
Okay.
So okay. Yeah, but I imagine there's a bit of learning curve to it as well. But if you think about it, just abstract yourself from asynchrony, and if you are familiar with synchronous link, asynchronous link is not much different. It just we used to do pull in for data with synchronous link. With asynchronous link, it's more like we expect a push. So we people who are familiar with reactive extensions will probably see a lot of common in this. So it's up to you to decide. I prefer language constructs. I prefer a wait for loop. I prefer async disposables. I prefer whatever language can provide me with.
I naturally fall back to that too. I can set a breakpoint on something and I can visualize in my head what's happening.
And that's how it's different from reactive extensions. It's easier to debug because it's actually kind of pseudo-linear. You can put a breakpoint, step through it. I like it.
Yeah. I had one other question, which is, when you're debugging, are there strange cases, or do you have any tips and tricks for debugging things when they're not working how you expect?
I would say there is no like trickery. It's that, and that's what I like about it. If you're familiar with synchronous debugging, I think Visual Studio does a lot of good work to give you the same experience for asynchronous debugging. There is a synchronous stack, and you can actually see like what it is like, that nesting level of asynchronous calls. So it's pretty nice. I didn't face any issues debugging this one.
Great. Okay. Well, we're just over time. So thanks a lot. Yep. Great. Appreciated your talk. I'll be checking this out later. Okay. Bye. All right, that was great. Well, we have a ton of great content tonight, and so we just learned about async and enumerables and all kinds of crazy mind-blowing stuff. And we're going to switch gears a bit, and we're going to be talking to Stefano. And Stefano has a really cool talk where he's going to be, this is some more kind of visual stuff here. Wait, I actually have even a banner that I'm supposed to pop up on here. Oh, it's custom vision, right?
It is custom vision, yes.
I'm excited to hear all about it. So I don't see your screen shared anymore. When you're ready to share that, we can pop that back up.
Sure thing. Coming through.
There it is. I'm going to add your screen and I'm going to disappear.
Okay. Thanks, John. And hello, everybody. Welcome to Bring Intelligence to the Edge with Custom Vision. I'm actually going to justify why custom vision with a few examples which I hope you enjoy. My name is Stefano Tempesta. I'm a CTO at Connecting Software, and I have signing different tags for it. So
they get sent sort of higher.
Excited about this next one. We are going to be learning about source generators from my friend David, and he's been, you've been doing all kinds of stuff lately. You wrote an online, like a web tool for evaluating source generators and using Blazor, right?
Yeah, that's right. I kind of beat Visual Studio to the punch, and the Visual Studio tooling wasn't ready yet, so I had to take matters into my own hands. But I'm glad to say Visual Studio has caught up and surpassed me, so I don't have to renew the domain next year.
Wow. Okay. Well, we're short on time, so I'll just turn it right over to you. So let's see what you got.
All right. Let's talk fast. Hello, YouTube. Hello, Twitter. Hello, everybody. Let's talk source generators. So source generation in general is something that's been around for many, many years, and there's lots of different ways to do it. You can use Codesmith, you can use T4 templates, you can write your own MS build tasks. You could do stuff after the compiler by using Foddy or PostSharp. What I'm going to talk about specifically is C#9 source generators, which is a new feature in the .NET 5 C#9 tooling that lets you do this, but as part of the compiler. So let's talk about what that means. This is the sort of highest level view of the C# compiler that you'll get. This is what happens when you compile your code. So you have your C# files on the left-hand side there, and they get sent into the compiler, and of course we get a DLL out the other end. But what really happens inside the compiler? There's a few different phases. Some of those, not all of them, are. So the first one is the parse phase, and what that does is it takes your C# code and it turns it into an object model, which is a syntax tree. In the C# compiler's case, it's called the concrete syntax tree. That's just because it contains every little bit of information about all the white space, about everything in your code, and you can go back from a tree to source code. But that doesn't matter. Essentially, this is just a series of C# objects that represent what's in your file. It doesn't have a lot of smarts about types and things. That comes later, specifically in the compile phase. So your syntax trees are sent into the compile phase, and that produces a compilation. A compilation has two things in it. It has your syntax trees, which is exactly what was in your code, and then it has your symbolic information. And those are the types that you're using. So when you use the keyword string, the parser knows that's a keyword, but it's up to the compilation to know, oh, well, that's a system.string, and here's the DLL it comes from. So what's cool with C#9 is if you have a source generator in the mix, what happens now after the compile phase is that compilation, so that syntax tree and those symbolic information, they get sent to a source generator. A source generator is just a DLL that you provide. You tell the compiler, hey, here's somewhere I want you to load source generators from. It can be whatever code you want because you just write a DLL. That source generator gets to run, gets to look at those syntax trees, gets to look at that compilation, and it generates a string, which is new source, and it can generate more than one. That new source gets parsed, becomes a syntax tree, gets compiled, becomes a compilation, and then that compilation is melded together with the compilation from your project to finally go to the emit phase and become IL, and then out the door to a project, to a DLL. So with C#9 source generators, what you can do is you can hook into the compiler pipeline and run some of your code, and you can access some of that internal data structures that the compiler has, which is super powerful. So at this point, usually people have some questions, and I'm going to try and guess what they are. Firstly, does the source you generate exist on disk? Not by default. You can do that. There is an option. It's called emit compiler generated files. This is sort of the first gut feeling what everyone wants to do is, hey, I've written a source generator. It generates some source. Let me see it. So that option is there for you, but you shouldn't rely on it. And in fact, I personally, and I've written a few of these, I've never needed it. I've never turned it on. And I'll show you in Visual Studio why you probably don't need it a bit later. Can you have multiple source generators? Absolutely. You can have as many as you like. One of the big sort of design considerations about whether C# source generators is the right choice for you is that source generators can't rely on each other. You can't have one source generator that generates, a bunch of classes and then expect another source generator to pick up those classes and do something with them. Each one is independent and they all contribute back to the main project, but they don't see each other's work. So that's a big design consideration that might rule this out as a solution for you. And that's fine. This is not meant to replace any existing technology. This is just another option. Do we really have to produce strings? So what happens is you start to write a source generator and you start to produce these strings and use a string builder, and then you have to output a quotation mark, and now I've got to double quote it. But what if I want to output a string in my source? Well, now I've got to double quote my double quotation marks, and it's a pain. There is other ways to generate source, but at the end of the day, you have to produce a string for a source generator because that is what the compiler is really good at compiling. That's what the compiler is hardened at compiling, so it's not going to crash. It's not going to expose any bugs. So yes, at the end of the day, you need to have a string. But there are other object models you can use, and then you can convert to a string just before you sort of add them. Can they change code? This is the other biggest design factor to consider that might rule this out as for your scenarios. They cannot change existing code. What is in the project that the source generator is running against does not change. It cannot be touched. This is very different to existing source generation options. So again, this is not meant to replace those features, but it is a very big design consideration you should think about. There's some little tricks you can do, I'll talk about later though, that maybe can help. And then how's the IDE experience? It's really good if you're consuming them, which is what most people are going to do. If you're writing source generators, it can be a little bit annoying because Visual Studio, being a .NET framework app, it can't unload DLLs. Therefore, if you have a source generator and you change it and then you expect Visual Studio to pick up the new one, that can be a little bit annoying. But for consumers, it's great. And it's going to get better for authors as time progresses. So what can you do with them? In my opinion, there's three basic buckets for the types of source generators people might want to create. The first one is with an eye to performance. So there's a lot of stuff where we do a lot of work at runtime via reflection. Maybe at app startup, we have to go and discover a bunch of stuff for a DI container, or for ASP.NET routing, for example, would have to do this to discover your controllers. If that work can be swapped to happening at compile time, right? If all of that data is present at compile time, then you're saving your users all of that time, and you're basically putting it on your build server instead of your users' machines, which is a huge benefit potentially. The other one is for processing external files. So source generators can access other files in your projects. And so you might use them to generate strongly typed wrappers for XML files or JSON files or CSV files. You can use them to even do, well, actually, I think I've got an example later. Talk about that then. And basically, at the end of the day, you can just use them to automate things. So if you're going to implement iNotify property changed, or you've got to create dependency properties for all of your normal properties, things like AutoMapper exist for this same reason. Sometimes it's just boring to write code, or it's repetitive, or it's error prone. And so potentially just the act of generating could be the win. Source generators can also report diagnostics. This is another huge win, particularly in the case where you're doing something at compile time instead of at runtime. So say you're building a DI container. If you're building a DI container and you don't have an implementation for some interface that is required, that's going to throw an exception at runtime, probably at app startup. If you can convert that to a source generator, you can break the build when someone forgets to check in an implementation. And that's a much faster way to detect these issues. Now, you can also write Roslyn analyzers. Don't use source generators to write analyzers. Analyzers still exist. But it is nice to know that as part of generation, if you find errors, you can report them immediately. So accessing additional files, I briefly talked about this. But basically, you can just access whatever is in the project that is added via an additional files element. A friend of mine, with that link down the bottom, he created a transpiler that takes a language that doesn't support .NET. You add the source code for that language as additional files. He wrote a source generator that is a transpiler that converts it to C#. Roslyn then compiles that C# into a DLL, and all of a sudden, we have a new .NET language. So you can do all sorts of wacky things with additional files. Partial methods. I'm trying to whip through this so I can get to the demo. Partial methods. So I said that source generators can't change code, and that's true, but there's tricks. Partial method is one trick to allow you to sort of augment a little bit the code. So partial methods have been in C# for a while, and the way they work is you define a method signature, you call that method somewhere in your code, essentially creating a hole that will be plugged in with some real code later. And then optionally, you can provide an implementation for that method. Now, it's optional, and if you don't provide an implementation, that method call just gets removed. And because of that, these method calls, they can't change anything. So they can't have return types, they can't have output parameters, they can't have access modifiers. In C#9, because we got source generators and because partial methods become so much more useful, those rules are completely flipped on their heads. You can now have return types, you can have output parameters, and you can have access modifiers. But if you have any one of those things, you have to provide a method body, which is fine in the source generator case because your source generator is going to provide that method body. So this is a way you can't change code, but you can sort of define a little hole here where you know a source generator will be able to fill in the gaps. And so in the middle of the method, you could call some really annoying method to write and have the source generator fill that in, and it's as though it had changed that method. It didn't really, but we can squint and pretend. So how do we actually reference them and define them? Well, it's pretty easy. So on the top left here, over here and over here, two different alternatives to reference source generators. One as a DLL, just with an analyzer element, and the other one as a project reference, but still telling MS Build that it's an analyzer type. And importantly, we say don't reference the output assembly. So when MS Build compiles this project, we don't actually want our consuming project to reference our source generator. It's not a dependency. You don't have to deploy source generators. They don't go anywhere, but we just need it to be associated essentially. And then the actual source generator, which is down here, is simply a net standard 2 project, references a couple of Roslyn packages from NuGet, no big deal. These version numbers, are not the current ones, but that's all right. And then to define the actual source generator, it's just a class that is tagged with this generator attribute. That's how the compiler sort of discovers the source generator. It implements iSourceGenerator, and then it just has 2 methods. One is initialize, where it gets given some context and you can do some initialization work. And then one is execute, which is simply generate some code. And all you do is you call context.addSource, give it a file name, doesn't have to be unique. It has to be unique for your generator. It doesn't have to be like unique to the project. So you don't have to go and calculate anything. It's not difficult. And you just give it a string that is the source. It's really that simple. This source generator here on this slide totally works. It generates a class called foo. Debugging can be a challenge. So there's a couple of different ways. Debugger.launch is the easiest way, but can be really noisy. It turns out if you're using VS, VS will compile your code quite often, and you might end up with lots of requests from the debugger to try and debug something. The other option is a generator driver, which is a class inside Roslyn. It's in the Roslyn SDK, and you can use that to run your generator. That's in fact what the compiler internally uses as well. And so you can use that to write some test console apps. That's why I usually start, where I write a generator, I write a console app, and when I hit F5, it's going to run my generator and it's going to output what I generated to the console. And I just use that as I'm starting up. And then you can, of course, use that to run unit tests and test your generator properly. I've got a couple of links there to put in. So source generator template is a little repo that I put together, and it's just got 4 projects in it that is the starting point to any generator I wrote. It's got a console app, which is like the product. That's the thing we're going to run our generator against. It's got a source generator, and it's got a test console app and unit tests, like I just described, that use generator driver. So I use that as a starting point. If you want to get more serious about things, Chris has written a product called Kitatas. Chris is the developer on the compiler team who wrote all of the source generator stuff. So he knows what he's doing. And Kitatas is designed to enable debugging of source generators and analyzers. It's an MS Build SDK. It's got a .NET Global tool. It's a much more well thought out system. And then sourcegen.dev, if you really want to just sort of play around and you without digging in too much, sourcegen.dev is that website that John was mentioning at the start that I wrote, and that is probably the easiest way to get going. You basically get two boxes on the screen where you can type code. One is the program, one is the source generator. You can see what it generates and you can see what it outputs. But let's do some demos because that's what we're all here for. So one of the source generators I wrote was for the Windows Forms repository. A friend of mine nerd sniped me and said, hey, our enum validation code is a little complicated. Could we use a source generator? And I had a look, and yes, we could. So this is the old code. This is what essentially my source generator is replacing. And if we have a look here, it's about 200 lines in this client utils class, and it has a bunch of these isEnum valid methods. And to call these, you have to pass in the type of the enum you want to validate, what the value you're validating is, what's the minimum value this enum could be, and what's the maximum value this enum could be. The validation itself is not very complicated. But the issue here is there's a bit of a tech debt issue, right? We have to keep updating these arguments. If we add something new to our enum, we have to find all the calls to isEnum valid for that enum and update the values that we're passing in to these things. Otherwise, our validation won't be right. To try to tackle that, in debug mode, there's this code here, which is down here, which validates our validation code. And this validation can be expensive and it can be a memory hog. So we have this caching and there's a max size for it. And if it's too bloated, it clears it out and then it has to start again. And all in all, it just gets a bit complicated. And there's a bunch of these overloads. So this one checks for maximum number of bits turned on using these bit operations. There's this one where you have to pass in the mask of all values. It's just a bit of a pain, and it's not that it's slow. It's actually fast, but it's had to do all these sort of hacky things to get it to be as fast as possible because we don't want our runtime validation to be slow. So what I did was replace it with a source generator, which is essentially this method call. So this method here does not exist. It is generated at compile time by my source generator. Now, what I can do in Visual Studio is I can right-click on it and I can say, go to definition, or I can press F12. Visual Studio knows how to read the generated source out of the compilation, and it shows it to me. So this is, you can see here, it says generated. It says, hey, you can't edit this. It's generated by this source generator. Let me just drag this over here and show you how cool source generator files are. So this method here is validating this simple enum type. That's this one over here. And you can see all it does is it casts the enum we want to validate to an int, and then it checks, is the int between 0 and 1? If it is, great, we return, no problems. If it's not, we throw an exception. That's all the old validation did. That's all this validation does. And so you look at that and you think, well, that's basically what the old one did. It's not very exciting. But watch what happens if I start to write a third value for this enum. As soon as I type the T or the TH, this 1 has changed to a 2. Now, I haven't saved the file, right? This isn't even committed to disk, but because the compiler is running inside Visual Studio, this validation is automatically up to date. So that tech debt issue I talked about is completely gone. As soon as you do anything to affect that validation, to affect what the source generator is going to produce, it will run again and it will be correct. So I can finish typing this, it doesn't change. If I set this to a 7, the validation changes. Now we're checking between 0 and 1 and we're checking 7. If I change this to be 14, we now have a weird enum, but that's okay. Our enum generator responds. So rather than having multiple different options for how to validate an enum and having to call the right one, we've got one method, it does whatever it needs to do. Rather than having complicated code or possibly slow code, like this the old code could have used and probably did originally use reflection to do this validation, and that would have been a bit slow. So this one, the code is as fast as it can be, to the extent of, it will even do one if check if it can get away with it. All of this is powered by the fact that your source generator accesses what the compiler sees, right? That's how it works as soon as I start typing without even saving. It's because it's accessing those syntax nodes that the compiler has produced in the parse phase. What that means is you get to be as efficient as possible. So not only is this a tech debt thing, this is also saving us work. You'll see here there's 2 validate methods, one for this enum and one for this enum. The interesting thing about this isn't that the source generator is finding the enums in this file and generating methods for them. It's actually looking at this code that I am running, and it is finding the calls to the validate method. it is finding exactly which enums I am asking it to validate. So if I comment out this line of code, that second method goes away completely. So talk about efficiency. We are generating the absolute minimum we have to get the job done. Imagine what this would have been with reflection, looking for, finding the enum type, pulling out the values, etc. And you start to see some really cool benefits. The really interesting thing about this is because this is accessing internal syntax trees, you can see my code here now doesn't compile. I haven't finished this method call. But my generator has actually generated the validate method already because the compiler has sort of constructed enough of its model that my generator can run. It can see the validate call, it can read the argument. The fact that it doesn't compile, that doesn't matter. So your generator is always going to be up to date. Let's have a quick look at how the generator works because we have some time. I've managed to be fast, hopefully not too fast, but I want to leave time for questions. So this is the generator. There's a couple of things to point out. So firstly, we have this stub. Actually, I should show this. What this is if I comment out both of these calls, and I can't do that because I need to press F12 first. There. If I comment out both of these calls, there's no validate method defined, therefore it won't generate anything. The problem with that is that as I'm typing in IntelliSense, I'm not going to see the validate method because it doesn't exist. I'd have to magically know to call it. So this stub method, this is a good practice to do to generate out. At the very worst, if you're not going to generate anything, generate the sort of the structure of what you might need. It just helps with IntelliSense and things. We have our initialize method, and in there, we do this thing called register for syntax notifications. What that says is, hey, compiler, every time you see a syntax node, tell this thing about it. We'll have a look at that in a minute. And then our execute is the thing that actually does the generation. And you can see here, we are pulling out our syntax receiver and we're going to work on it. So the syntax receiver is this thing. This has one method. It says on visit syntax node, which is essentially called every single time for every node that the compiler sees. And so all we do here is we collect up what we're interested in. This is a very common pattern with source generators. Collect what you're interested in and put it in an object model. Then process that object model and put it into a better form, and then finally take that form and generate a string from it. But so here we're just saying, hey, if this node is an invocation, now this is an internal Roslyn type that is a method invocation. Looking at the syntax nodes, if you look at them with the debugger, the various syntax visualizers, if you use SharpLab has a syntax tree visualizer, you start to get the feel for how the language fits together, and it's relatively easy to understand for the most part. There's a few little edge cases, but there's plenty of good talks on that as well. But so we say, hey, is this a method invocation? Does it have less than or equal to 2 arguments? Because we know our validate method has 2. Is it for a method called validate? Is it on a type called enumValidate? Like, we're just narrowing down our scenarios. Is this a node we're interested in? And then if it is, all we do is